Good day, everyone. I'm 𝘂𝘚𝘩𝘳𝘯𝘵 from Department of CSC at SRMISC and Cognitive Applications Research Lab, and I'll be presenting this research work on American Sign Language prediction with extremely low memory footprint for edge devices. I have done this work with my colleagues 𝘍𝘠𝘠𝘠 and Stuti Sehgal from the same university and lab. Without further ado, let's talk about the problem statement. There are 500,000 ASL users all over the world, and there are no cheap and portable devices to recognize American Sign Language. So now imagine that you have a friend who communicates by ASL and you do not know ASL, you want to communicate with this person. We do have AI solutions which can recognize ASL, but they are very expensive or very complicated to use, etc. etc. Hence, we propose a novel method to deploy this detection technique on the edge. We use TinyML with post-training in 8-way quantization, and their model is just 185 kilobytes of RAM on ARM Cortex-M7 based microprocessor, and the inference speed is at 20 frames per second, which is quite great. The size of the model, which is 185 KB, is actually very small compared to other models which exist on the market. Maybe we have ResNets, which are about 50 megabytes, even the smaller versions. We have SqueezeNets, which come to about 5 megabytes after quantization. So we have tried to bring this to such a small size, and we'll discuss more about how great this advantage is in the later part of the presentation. But first of all, let's cover some of the prior work which has been done. So we do encourage you to go through the complete paper as it covers a more in-depth literature survey. But here we have shown just 6 papers in this presentation which we found to be of particular interest to us. The first paper here by 𝘂𝘠𝘠𝘠, MC.Liu and Z.Jane in 2015, it used Microsoft Kinect sensors. These are highly accurate, but for this you need to buy the Kinect sensor, and you don't usually carry a Kinect sensor around with you. So it's very expensive, computationally heavy, etc. The second and third papers here by Chopok and Chong, these are using leap motion sensors, which are basically 3D non-contact motion sensors or depth sensors, etc. in layman's term. These are, on the flip side, again computationally expensive, quite heavy, computationally heavy, etc. And not everyone can afford it, nor does everyone have a leap motion sensor in their house. But there was a pro which we found to be of particular interest in the third paper, especially because they worked for both characters with and without motion. For those of you who know ASL, you would recognize that the alphabet Z or Z for Zulu and J for Juliet. These two alphabets, if you want to sign this or finger spell this in ASL, you need to use some motion. But since we are working with images, we cannot detect these. But since they use the sleep motion sensor, they were able to detect or consider these characters which require motion for detection as well. The first paper on this slide by 𝘂𝘠𝘠𝘠 and MC.Liu again, it's from 2005, it's quite back in the day, but their approach was really innovative. So they use something called cyber gloves, which is actually like a glove which you wear, and it tracks the position of your fingers using an extra elaborate equipment as well. Again, it's very expensive and it's absolutely impractical outside lab conditions because you would neither be having this elaborate equipment to detect that you are wearing the glove, nor would you be having this glove in the first place. The second paper by D. Rathi in 2018, they use transfer learning. They use an Inception V3 network and also a mobile net network, and they compare the performance of both of these models which they train for the detection of the ASL task. It was detected that MobileNet was about 2% more accurate, like the differences were 93%, accuracies were 93% and 95%, if I remember correctly. Thus, the pro is that it's very highly accurate, but on the flip side, computationally very heavy, and mobile nets or Inception V3s are all very huge networks, non-suitable for most edge devices. Now, when we are talking about edge devices here, we are not talking about smartphones or Apple watches, etc. We are talking about something maybe of the shape of a small watch. We will come to this motivation part in the next slide itself. But first of all, let me tell you about Gheda and Radpur's work in 2017, who used deep convolutional neural networks very much similar to us, and they pointed out a lot of potential pitfalls, like a researcher who is trying to solve the ASL problem using deep CNNs. They point out like what are the various things which you should consider, what are the various things which can go wrong, which really helped us to like planar research and go ahead in a smooth way. They also pointed out that accuracy could be improved in their model, which we wanted to particularly work on, and I believe we successfully did that as well. Now let's come to the motivation. And I was telling you about the watch in the previous slide. Let's discuss that as well. Because every research needs a good reason, like why are you starting to do this work? So the goal we had was to make ASL more accessible and to enable the deaf and mute community to easily communicate and everything to be more easily accessible. Previously proposed methods, as we saw, were using either very expensive or computationally heavy solutions, or they were using transfer learning based solutions, which again would not run on edge devices, which we plan to use. So our goal or our dream here is to have a device, something like a watch, which can have a tiny little camera where the knob of your watch is. So if you want to detect what someone who is speaking in ASL is saying, you can simply point your watch or the knob towards that person, and this watch-like device or the watch-shaped device can easily transcribe this person's finger swelling to either speech or text or even braille, because nowadays many watches do come with braille support. So again, we are planning to keep the price as low as possible. So in INR, we are considering something like under 2000 rupees. And the plan or the hardware architecture which we have planned does allow that. So the user can see their hand signs transcribed to text and their speech in real time. And most importantly or interestingly, in this research work, we have done appropriate generalization testing to see how it would perform on images which are from a very different distribution or from say a different data set or a different background, etc., and how it would perform in real time, which is often not considered in research. The motivation, to sum it up, is that the proposed model that we have presented is tiny enough to run on even the smallest and cheapest of microcontrollers on wearable IoT devices. For the proposed methodology, let's first talk about the hardware which we are using. So we have a 32-bit ARM Cortex M7 based microcontroller, STM32H743VI. We have 1 MB of SRAM for onboard applications, 2 megabytes of flash memory for storage, clock speed of 400 MHz, and a frame buffer RAM of 496 kilobytes. It's used for loading the camera images, the model, scratch buffer, everything. Now, in the documentation, it was suggested that we could be using a model and a scratch buffer and the 400 KB, but from our experimentation, we determined that a model of even 230 KB failed to load, and the largest model which we successfully loaded was of 220 KB. So now this serves as a guide to other researchers working in this area, because if you are planning to load an image or a model of say 400 KB, that would not work for this board. Let's talk a bit about the dataset construction. This has been described in great detail in the research paper, and I will not go into great detail right now here, but I will definitely cover some of the key aspects. We used 4 datasets. The first one is SignMNIST dataset. You can search for it on Kaggle itself. The dataset has 1704 uncropped color images. So after removing alphabets like J and Z, which we have done for all the datasets actually, and also things like space, nothing, and delete, etc. So we got 27455 images in the training and 7172 images in the testing. Similarly, for the modified Kaggle ASL dataset, we got about 3000 images per class. So we have 72,000 images for training and 24 images for testing. We actually created a third dataset on our own. So we created 24 images, we created 400 images for each of the 24 classes. And now here you would see something interesting. We actually split it into 10% for training and 90% for testing. So our testing dataset is composed of 8640 images, and 960 out of those 9600 images were taken for training. So why this sort of a weird data train test split? Because we wanted to keep the test dataset as different as possible, but keeping the test dataset completely different did not really make sense, because then we were training on one distribution and we were testing on a completely different distribution. But again, that thing is called generalization, and we did want to test it out. That's the reason we took the Kaggle ASL alphabet test dataset created by Dan Rasband, and that has only 720 images from very noisy backgrounds, different cameras, different backgrounds, outdoor images. So we consider the accuracy we are getting on that as a generalization accuracy. Great. So now that we have covered about the dataset construction, let's get into the proposed architecture. Our proposed architecture uses CNN-based approaches. Everything was designed in TensorFlow 2.3. We use standard categorical cross entropy. We use Adam optimizer with the default learning rates, and we use callbacks to like reduce LR on plateau, model checkpoint, etc. Each weight was quantized to integer 8 and was as 1 byte. And complete size of the quantized model and weights as discussed was 185 KB. So this is the size of the combined model and the weights. This is a visualization of the network which we created. On the left, you see the float32 model. On the right, you see the integer 8 quantized model. The primary difference between these two is that you have the quantized step at the first and the dequantized step at the last. Other than that, the models are obviously the same. Now, we also did something else which is quite interesting. We tested what sort of augmentation techniques would actually work. Standard augmentation techniques like plus minus 20-degree rotation, random cropping, 20 cross 20 crops, followed by resizing to 20 cross 28 were done for model 1. But for model 2, this resizing part was done by the 5 image interpolation techniques in OpenCV, namely internearest, interlinear, interarea, intercubic, and interlength source. So finally, from model 2, we got a little over 10 to the power 5 images and testing set of 23,600 images. And just to compare that this second augmentation is actually better than the first augmentation, we have to make sure that the training and testing set and all other things are kept constant. Hence, for model 1, we actually augmented it a lot more till it reached the exact same value. And for the train set, the test set, and the model quantization was also done in a similar way. We would later see that the model 2's augmentation technique actually works much better. Let's look at the results here. So the confusion matrix for model 1, as we see, since most of the most of the outputs are along the primary diagonal, this is a good signal. But you see that once it's quantized, when the predicted label is G and the actual label is H, there are 410 cases which is wrongly predicted in int 8, but not in the case of float32. So these things are massively reduced when we are using the model 2 or the second method of augmentation. Again, these are just the accuracy and loss curves for all the 40 epochs of which we trained both model 1 and model 2. These are some sample predictions and most of them are right. But here I would like to draw your attention to the first row and the fourth column, where the true in model 1, here we see that the true class is B, but for both float 32 and int 8, the prediction is the letter T for tango. But in model 2, all the predictions are correct. Similarly, in the last row and fourth column, we have the true class is A, float 32 prediction is also correct, it's A, but after quantization it becomes Y. But in model 2, all the predictions are correct. So performance metrics, let's come to this. We can see here that the model 1 performs better in terms of test accuracy, and model 2 performs better in terms of test accuracy and also generalization accuracy. We'll come back to this chart, this table, as we cover the findings as well. I would correlate the table with all of you. First, let's discuss the strengths of the proposed algorithm. It's extremely efficient, real-time, well-generalizable CNN-based approach implemented on an ARM Cortex-M7 based microcontroller. Test accuracy for model 2 was 90.84 and 74.58 was the generalization accuracy. Interpolation was found to be the most efficient way of image resizing and augmentation. And we also proved that model performance seems to be much better with Flow32. It is, however, well known, but our research findings are corroborated by according to this knowledge. So to sum it up, let's talk about the primary findings of our research. Interpolation reduces a drop in accuracy during quantization. So if you go to this table back here, you would see that interpolation has been used for model 2 and the drop in accuracy is just about 0.2 from the flow32 to the int 8 model. But for model 1, the drop in accuracy is almost 3%, which is quite significant. Secondly, we found out that flow 32 inputs and outputs give best results. And thirdly, we saw that interpolation augmentation improves classification generalization. How do we see this? In model 2, the classification the generalization accuracy for classification is about 74.58%, but for model 1 it's about 70.97% lesser. Thus, we conclude these three primary findings of our research.